We are excited to present RDFace, a benchmark dataset for rare disease facial image analysis under extreme data scarcity and phenotype-aware synthetic generation. Rare diseases are individually uncommon, but collectively affect a large population worldwide. More than 10,000 rare diseases have been identified, and many pediatric genetic conditions present with distinctive craniofacial phenotypes. In low-resource settings, facial images may be the only accessible cue for pediatric early diagnosis. However, building reliable AI systems in this domain is difficult for 3 reasons. First, data are extremely scarce. Many conditions have only a few publicly available patient images. Second, different rare diseases can share highly similar facial features, making fine-grained recognition difficult. Third, ethical and privacy constraints limit large-scale data collection and standardized benchmarks. These challenges motivate the need for a transparent benchmark that reflects real-world scarcity rather than assuming large labeled datasets. To address this gap, we introduce RDFace, a curated pediatric rare disease facial image benchmark. RDFace contains 456 facial images spanning 103 rare genetic conditions, with an average of only 4.4 images per condition. This makes RDFace an ultra-low shot benchmark by design. Each image is associated with standardized metadata, including disease name, gene information when available, disease abbreviation, disease subcategory, and orphanet code. To improve reliability, candidate diseases were cross-verified with orphanet, and image label associations were reviewed for clinical plausibility. The dataset also captures demographic and geographic diversity where information is available. RDFace supports 2 main benchmark settings. The first is standard supervised classification. We evaluate 6 pretrained vision backbones. All models are trained under a consistent protocol and evaluated using top K accuracy across 103 disease classes. The second is few-shot learning, where we use prototypical networks under 5-way, 10-way, and 15-way one-shot settings. This setting evaluates whether models can generalize when only one support example is available per disease class. Together, these 2 protocols evaluate both conventional supervised learning and data-efficient recognition, which are both important for rare disease AI. Because real data are scarce, we further study whether synthetic facial images can help improve recognition. Before generation, images are enhanced using super resolution and colorization. We then compare 2 generation strategies. The first is DreamBooth, a class condition diffusion model fine-tuned separately for each disease using the available real training images. The second is FastGAN, an unconditional few-shot generative model trained on the processed image set with all training samples. After generation, a central contribution of RDFace is the Phenotype-Aware evaluation framework for synthetic images, where synthetic samples are evaluated using at 3 levels. First, we use retina face detection to evaluate the visual realism of images generated. Second, facial landmark similarity and LPIPS perceptual similarity are used to compare synthetic images against real class prototypes. Third, we use a vision language model to generate phenotype-style facial reports from real and synthetic images, then measure semantic similarity between the reports. The key goal is not simply to generate more images, but to determine whether synthetic images preserve disease-relevant facial structure. Our experiments show that rare disease facial recognition remains highly challenging. Using real data only, models can often narrow the candidate space, but exact diagnosis remains difficult under extreme scarcity. Synthetic augmentation shows a clear difference between generation strategies. DreamBooth improves performance across most backbones, while FastGAN often reduces accuracy. This suggests that class condition generation is important for preserving disease-specific cues. We also find strong semantic consistency between real and DreamBooth-generated images, with VLM-based phenotype report similarity reaching 0.8404. In summary, RDFace provides a transparent benchmark for rare disease facial image analysis under realistic data scarcity. We hope RDFace will support future work on interpretable, data-efficient, and clinically responsible AI for rare disease diagnosis. Finally, we gratefully acknowledge all of our sponsors for their generous support and contributions to this work. Please scan the QR code in the bottom right corner to visit our project page for the dataset, benchmark details, and code. Thank you for your attention.